So in the last video, you got done all the definitions related to particle motion. I kind of justified some of those to you. In this video, we're going to take a look at 3 examples of how to use those definitions to analyze the motion of a particle. For our first example, a particle is going to move along the x-axis with a position given by the function s of t equals t cubed minus 5t squared plus 2t plus 7. And this is valid when t is greater than or equal to 0. We're going to go through a bunch of different parts of this problem to analyze this, but before we get started, please take a moment and just copy that down. First thing we're going to do, we're going to find the velocity and acceleration functions. We're going to go and we're going to find the velocity and acceleration functions. Remember that the velocity is the derivative of the position. Acceleration is the derivative of velocity, or the second derivative of position. Take a moment, create those formulas, and let me know what they are. We should get a velocity equal to, let's see, derivative of t cubed is 3t squared. Derivative of minus 5t squared is minus 10t. Derivative of 2t is 2. The acceleration, let's see, derivative of 3t squared is 6t. Derivative of minus 10t is minus 10, and we've got our acceleration. Before we move on, though, to deal with the other parts, what I'd like to do is make some number lines for my velocity and my acceleration. Because so many of those definitions involve the velocity being positive or the acceleration being negative or various things like that, if I can make a number line for these things and get a sense of when each is what sign, it's going to save me a little bit of time later. I'm going to go and make a number line for my velocity. I'm going to put a boundary at 0. I'm going to label this v of t. Remember, always label your number lines. I need to go find my critical values. Well, that involves setting the velocity equal to 0 and solving. Well, you know what? Here, since it's a quadratic equation, why don't we just use the quadratic formula? If it wasn't so easy, we'd have to do some solving by graphing. Take a moment and get your critical values. I want to say that, yeah, why don't we, because we may end up plugging some of these things in later, I should probably give decimals that are accurate to more than just 3 places. So I'm going to say we have 1 at 0.213700. The other one is going to be 3.119633. By the way, in case you didn't realize this, we're using our calculator for everything in this section as well as that last section. We now need to go test our regions. Well, plug in something like 0.1. Go use your calculator. What happens when you plug in 0.1? I think that region should be positive. Plug in something in your second region. What sign do you get there? I think that should be negative. Plug in something in the last region. What sign do we have there? I think that should end up being positive. As for my acceleration, well, when I set this equal to 0, I get 6t equals 10 divided by 6t equals 10 over 6, or 5/3, 1.6 repeating. I'm going to try to align my 2 number lines. It's going to make some of our work moving forward a little bit easier. I'm going to put my 5/3 right over here. Take a moment and go test your regions. Sign of that first region, you plug 1 into the acceleration. 6 times 1 minus 10 is something negative. Plug in 2. 6 times 2 is 12, minus 10 is something positive. And we've got our number lines. We'll use those more in a little bit. Part B. Find the initial, position, velocity, and acceleration. Find the initial position, velocity, and acceleration. Now, if we want to do that, what would we have to do? All we have to do is plug in our initial time, our time of 0, into the position, into the velocity, and into the acceleration. Take a moment, go do those three. Okay, make sure you're showing your work with these. 0 cubed minus 5 times 0 squared plus 2 times 0 plus 7 is just going to be 7. V of 0 is going to be 3 times 0 squared minus 10 times 0 plus 2 is going to give us 2. 6 times 0 minus 10 is going to give us negative 10. Initial position is 7. Initial velocity is 2. Initial acceleration is negative 10. Part C. When is the particle moving right? And I want to justify my answer. Just like our curve sketching stuff, with particle motion, we're also going to have to justify things. Oops, hold on, I didn't actually finish that question. When is the particle moving right? Well, what's our definition of a particle moving right? The particle's moving right when our velocity is positive. All I need to do is go look at my number line over here, and I think I'm going to be moving to the right from time 0 to 0.21 here. I'm just going to give 3 places. 214. This could be a parenthesis, doesn't matter. Either way would be okay. And then again, I'm moving right between time 3.120 and infinity. Why? Because v of t is positive. That's what we're going to do for that. Before we go on, I would like you to take a look at the activity link posted in Google Classroom that will bring you to a little particle motion demo that I put together. I'd like you to go type in your position function and push play and watch the particle move along the x-axis. And I'd like you to see if it starts up by moving to the right for just a split second, then moves left, and then moves right again from time 3.120 until the end. Take a moment and test that out. Hopefully you saw the particle doing what we just calculated it to do. And we're going to keep going back to this demonstration as we analyze other parts of our particle motion stuff here. Part D. When is the velocity decreasing? And again, as always, we will justify our answer. When is the velocity decreasing? Well, what do you remember from the last video? What's our definition? Last video or your last page of notes. Go flip back if you need to. What's our definition of velocity decreasing? Remember, this is different than slowing down. Velocity decreasing is when the derivative of velocity, our acceleration, is negative. So I'm going to go check out my acceleration number line. I think our acceleration is negative between time 0 and time 5/3. So that's what I'm going to say. When is the velocity decreasing? Between time 0 and 5/3. Because the derivative of velocity, which happens to be my acceleration, is negative. Velocity is decreasing when the derivative of velocity, which happens to be our acceleration, is negative. Part E. When is the particle slowing down? And again, we'll justify this. When is the particle slowing down? We're going to justify this. What's the definition of the particle slowing down? I hope you realized this is a different question than Part D. Part D, the velocity is decreasing, which means our velocity goes from 20 to 15 to 12 to 11, or so on. Or from -2 to -4 to -10 to negative whatever. Particle is slowing down. Our definition is the velocity and acceleration have opposite signs. Well, let's see. I'm going to try to pick out the regions where they have opposite signs, and this is sort of why I made my two number lines stacked with tick marks that match up. You know what? How about you see what you can do? Tell me where the particle is slowing down, because velocity and acceleration have opposite signs. If we've got this in our first region between 0 and 0.214, then they're both negative for a while. Then between 5/3 and 3.120, I think they have opposite signs. That's what I'm going to say. Between times 0 and 0.214. And then again between, I realize it looks weird to kind of mix fractions and decimals. If you really don't want to do this, you can make it 1.6 repeating. But 3.120. What's our reason? Because V of t and A of t have opposite signs. I'm going to pause for a moment so you can get that copied down. And actually, before we go on, take a moment, take a look at this in the little GeoGebra demo, see if we're really slowing down initially, then speeding up, and then slowing down again between time 5/3 and 3.120. Check that out. Okay. Next, letter F. Find the average velocity. Over the interval from time 2 to time 5. We want to find the average velocity between time 2 and time 5. As we said in the notes, is the average velocity the change in position over the change in time, or the change in velocity over the change in time? Should be change in position. Should be position at time 5 minus position at time 2 over 5 minus 2. Take a moment, go calculate these, because this is S, you're plugging into your position function, and then tell me what the average velocity is. Let's see, position at time 5, I'm going to go plug into my calculator, 5 cubed minus 5 times 5 squared plus 2 times 5 plus 7. I'm getting 17 for that one. Minus position at time 2. I'm getting -1 for that one. Over 5 minus 2, this looks like 18 over 3. Hopefully you sent in an answer of 6. My average velocity is 6. Remember, this now is velocity over an interval rather than just at 1 split second. One more part to this problem. Let's see. Letter G. I think I may have to flip back to the other side. Let's see here. Letter G. What is, oops, you can't see that, sorry about that. What is the furthest? Left or right that the particle goes over the interval from 0 to 4. And when we're done, as always, we'll justify this. Take a moment, get that copy down. Furthest left or right that the position goes, Well, that the particle goes, that's referring to the position. In particular, I want to find the absolute maximum and or minimum position. I want to find the absolute maximum or minimum of my position function, s of t. Step number 1, I need to find critical values, which means I'm going to set the derivative of position, or velocity, equal to 0. You know what? We already did this. That was where I got those values from setting the velocity equal to 0. So I'm just going to take those values. This is actually why I gave so many decimal places with them, because we're going to have to do some plugging in. I'm going to say t equals 0.213700 and 3.119633. And to find the absolute maximum or absolute minimum, that means candidate's test. So I'm going to set up my table of values over here. I'm going to say time. I'm going to say position, because I'm plugging into my position. I want to know the position at my various times. I'm going to include my endpoints and my critical values. I don't think I made this quite big enough. 0.213700, 3.119633, and time 4. And then I need to find the position. Actually, we can use the table feature on our calculator to do this. Finish copying that down, and then push continue, and I'll show you how to use this on the calculator. Okay, so the first thing I need to do, I think I've showed you this with other things, but just as a refresher, we're basically going to create a table on our calculator. Clear out whatever's in Y1, and type in your position function, just replacing the t with an x. So x cubed minus 5 times x squared plus 2 times x plus 7. Then go to second table set. I want the independent variable, the x, or really the t, to be changed to ask. And once you do that, do second table, and you should get a table with nothing in it. Now, all we're going to do is type in our times. I'm going to say 0. I'm going to say 0.213700. And I'm going to say 3.119633. And I'm going to say 4. Well, it's giving me the positions. Although I realize one of them is under that smudge on the calculator. I can't totally see, but it's a 7. That's okay. Let me copy these down. I've got a 7. I've got 7.2088. I've got negative 5.6, nope, sorry, negative 5.061, and negative 1. Well, my furthest right position is going to be my absolute maximum. My furthest left position is going to be the absolute minimum. The furthest right that the particle will reach on my interval from 0 to 4 will be the tick mark at 7, well, not really a tick mark, near the tick mark, 7.0, oh my goodness, wow, 7.2088. The furthest left, well, that's the other one. I'm going to go with negative 5.061. If I was asked when it reaches those times, when's it the furthest right? At time 0.213700. When's it furthest left? At time 3.119633. Take a moment, go back to that GeoGebra demo. Change your time interval so it just goes between 0 to 4. Then run it and check these things. Check to see if the furthest right it goes is 7.2088. Check to see if the furthest left it goes is negative 5.061. And hopefully you saw it do what we want it to do. Let me show you another example. Let's see here. Okay, another example. I'm not going to write down all the details. I'm just going to give you a position function. I'm going to say s of t equals 3 times the sine of 2t minus 4 times the cosine of 3t. I'd like you to go and create the velocity function. Let's create our velocity. We'll check it. We'll create the acceleration. We'll check it. Then I'll give you probably 3 different problems to take a look at involving analyzing those. Your velocity should be your derivative of position. I really, really hope when you did this you used the chain rule. We're going to get 3 times the cosine of 2t times 2 minus 4 times negative sine 3t times 3, which gives me a velocity of 6 cosine 2t plus 12 sine 3t. And that's my velocity function. Go create your acceleration, again, keeping chain rule in mind. So my acceleration is my derivative of velocity, 6 times negative sine 2t times 2. Let's see then, plus 12 cosine 3t times 3. So we're going to say that our acceleration equals negative 12 sine 2t plus 36 cosine 3t. And hopefully that's what you got and sent into Edpuzzle. 3 parts to this one. Is the particle moving left or right at time t equals 2? And we'll justify. I don't have room to write justify, so I'm just going to say why. Is the particle moving left or right at time t equals 2? Well, to figure out left or right, what does that involve me looking at? The position, the velocity, or the acceleration? Hopefully you said the velocity. I could make my number line and do all of that, but there's an easier way to do this. Rather than going through all the number line work, since I don't care about figuring out the intervals where it's moving left or right, but just care about what's happening at time 2, all I'm going to do is plug 2 into my velocity. I'm going to find v of 2, which is 6 times the cosine of 2 times 2, plus 12 times the sine of 3 times 2. Go set your calculator in radian mode and tell me what the velocity at time 2 is. Let's see here. Okay, I'm going to make sure I'm in radian mode. I'm going to do 6 times the cosine of 4 plus 12 times the sine of 6. I am getting negative 7.275. So what? Am I moving left or am I moving right? Since my velocity is negative, I'm moving to the left. I'm going to say moving left, because the velocity at time 2, not v of t, but v of 2, is negative. Moving left, because the velocity at time 2 is negative. Make sure you show what that velocity is. And then tell me left, because v of 2 is negative. I guess you could also say v of t is negative at t equals 2, but that's more writing. I think v of 2 is negative is the way to do it. Don't, though, just say v of t is negative. Part B. Is the particle speeding up or slowing down at time t equals 2. Why? Is the particle speeding up or slowing down at t equals 2? Why? How are we going to figure this one out? Speeding up or slowing down means looking at the velocity and the acceleration to see if they have the same sign or different signs. Well, I already know my velocity at time 2 is negative, so let's go find our acceleration at time 2. You go do that. What's the acceleration at time 2? Let's see, this is negative 12 sine 2 times 2 plus 36 cosine 3 times 2. Okay, so negative 12 sine 4 plus 36 cosine 6 should give us, I believe, 43.648. Well, velocity is negative, acceleration is positive. What does that mean? Speeding up or slowing down? I think that should mean slowing down. We're going to say slowing down because v of 2 and a of 2, make sure again you're referring to that t equals 2, have different signs. We're slowing down because v of 2 and a of 2 have different signs. Take a moment, finish copying that down. Running out of room on this sheet. How about I do this? Why don't I come over here? I want to keep some of this on the screen. Oh, that didn't quite work. Zoom out a little, maybe. I don't know. Whatever. I'm just going to start writing part C over here, and we'll see what happens. Is the particle moving towards or away from the origin, x equals 0, at time 2? And of course, we'll then ask why. Is the particle moving towards or away from the origin at time t equals 2? Copy that down. I already know my particle is moving to the left. Here's my number line. Here's the origin. If I'm moving left, am I moving towards the origin or away from the origin? Or can you not just answer that knowing that we're moving to the left? Actually, let me ask a different question. I don't think we can tell just from the fact that I'm moving left if I'm moving towards the origin or away from the origin. What other piece of information are you going to need? I think I need to know the position of the particle at time 2. If I'm somewhere over here and moving left, then I'm moving towards the origin. But if I'm somewhere over here and moving left, then I'm moving away from the origin. Let me go find s of 2. Actually, I'm not going to. You're going to. Go find s of 2. Tell me the position at time 2. Let's see. This is going to be 3 times the sine of 2 times 2 minus 4 times the cosine of 3 times 2. So 3 sine 4, rather, minus 4 cosine 6. Getting negative 6.111. I'm over here. I'm moving left. What does that mean? Towards the origin or away from the origin? I think I'm moving away from the origin. I am going to say away. Let me move this up a little bit and zoom in. I'm going to say away from the origin because let's see. How about we say because the particle is to the left of the origin, how do I know that because s of 2 is negative, and my particle is moving left. Take a moment, copy that down. I completely forgot to have you get this position function into that GeoGebra app that I sent you earlier and kind of test these things. Put that initial position function in there, then run it and see what's happening at time 2. Are we moving left or right? Hopefully we're moving left. See what's happening at time 2 again. Are we speeding up, slowing down? Hopefully it's slowing down there. And if we're moving towards the origin or away from the origin. Go test this stuff right now. Okay, I have one more thing to show you, assuming I do have the right piece of paper. Can you take a moment and please take out from your packet of in-class examples a sheet titled Particle Motion Problem. Zoom out a little bit so we can see the whole thing. Go get that sheet out. I'll wait a moment. Particle P moves along a horizontal line. The graph below shows its velocity as a function of time. So this is not the position, this is my velocity. You know what? See if you can go do A and B. I think you can figure those out. What is the velocity at time 1? Velocity at time 1, this is the velocity. I'm just going to look at my y-coordinate over there, my velocity, 0. To find the acceleration, that means I need to find the derivative of velocity, which means I need to look at the slope. What is the acceleration, the derivative of velocity at time 1? Well, let's see here. This looks like down 2 over 1. I think my velocity, not my velocity, my acceleration, my slope of velocity is negative 2. The y values here represent my velocity. The slope here, the derivative of velocity, is the acceleration. With that in mind, see if you can handle C. We'll just do C. Then we'll do D in a moment together. Try C. The particle's moving left when the velocity is negative. Well, I think the velocity is negative between time 1 and time 3, and then again between time 3 and time 5. So I'm going to say 1 to 3. And then 3 to 5. I'm not going to include 3 because it looks like it's stopped right at time 3. It looks like my velocity is 0 there. For my justification, because v of t is negative there. Can you figure out where we're speeding up? We're speeding up where our velocity and acceleration have the same sign. My velocity here is positive, and my acceleration, the slope of this, is negative, so it's not going to happen there. But I think between time 1 and time 2 will be good. My velocity is negative, and my acceleration, my slope of acceleration is negative. So I'm going to say between time 1 and time 2. Then I have negative y values, but a positive slope. That doesn't count. Oh, this one's good. Negative y values, negative slope. Negative y values, positive slope. That doesn't count, but here's another one. Positive y values, positive slope. Between time 1 and 2, 3 and 4, 5 and 6, because v of t and a of t, which is just the derivative of my velocity, have the same signs. Take a moment, finish copying that down. I think this is about all I have to say about particle motion for right now. I've kind of shown you all the different variations we can deal with so far. We are not done with particle motion. This is going to keep coming back throughout the year as we learn about integration, This will be one of the first applications of integration we look at. And we'll definitely add a few more tools to our list of things we can analyze. But for right now, I think we're going to stop here.